Hello, everybody, and welcome to a webinar on bearing alignment. You can see on our screen here, you have our personal cell phone number, so you guys can call us and take advantage of our expertise and our email addresses. So jot those down, and let's go to the next slide. So Morel is not only just a distributor, we are an engineering partner, a systems integrator, and a value-added distributor. And you can see our territory there at the map around the Great Lakes region. And the advantage of using our expertise is we do this every day. So when you guys are on the front end of design, give us a call and we can help make recommendations so that your design goes smoother, easier, and we will pick the best costs and optimal solution for what you are doing. Let's go over the agenda. We're going to go over moment loading on actuated linear guides, accuracy levels, reference edges, best practices, mounting illustrations, and tolerancing alignment, best practices. So let's start with moment loading. I am excited. Here we go. So for single rail, single block solutions, you are looking at a moment loading diagram in the right-hand upper corner of your screen, and the moment load comes around the center of the block. So you have moments in three directions: along the x-axis, which is the roll moment, along the y-axis, which is the pitch moment, and along the z-axis, which is the yaw moment. So you can think of this as the same way a direction of an airplane works. And if you look at the two red arrows, you'll see moment loading ratings. So the 0 is the static moment loading rating, and the MTML is the dynamic capacity used in the bearing life formula. Next. So you can see three diagrams here, and you see a little green cylinder that goes around as the origin of our coordinate system. So in figure A, you have a single block, single rail system. This one has the least amount of moment loading capacity. When you add an extra block, figure B, on a rail, you actually increase the yaw moment of the system and you increase the pitch moment of the system, MZ and MY. And when you add another rail and another block in the other direction, figure C, you increase the yaw moment and the roll moment of the whole system. And you can see that coordinate system. It originates from the center between the two rails. In figure D, this is the most common system that you'll see in the linear bearing world. You'll see two rails, four blocks. The coordinate system moves into the center of it all. And this one gives you pretty good moment loading capacity in every direction. Figure E is mainly used as a 6-runner block system. It's mainly used for adding additional load, but the two center blocks really don't give you too much additional moment loading. It kind of acts like a teeter-totter. So, but it will give you additional load capacity. Optimally, you want to move to figure F, which actually has 8 blocks. And by spreading out those 4 in the middle, you actually get a reasonable increase in moment loading on the system capacity. So for actuated linear guides, where we provide everything in a single system, it's similar to the diagrams. So I'll show you a couple examples. On the left, you'll see a linear module from Bosch Rexroth, which is a single rail system. You can get either 1 or 2 runner blocks on the carriage. And you see the coordinate system then moves into the center of that carriage. So if it was a single rail, single block on the carriage, it'll be just like a 1 rail, 1 block system. If there's 2 runner blocks on there, it'll be like a 2 runner block system. And in this system, the drive's all built into the extrusion. And this extrusion is pretty beefy. It's built big enough to take deflections and act as structure. The one on the right, it's a compact module. This is our best seller. It has 2 rails inside of it, and you can get 2 rails, 2 blocks, or 2 rails, 4 blocks as a standard. And this can take even better offsets because it has the 2 rails, 4 blocks option. And then for gantries, we can really play around with the spacing of all this. So as you space rail to rail, as it gets wider, you add moment capacity. And as you space block to block wider, you add moment capacity. So we can take actuated linear guides and take single rail systems and space them apart, take double rail systems and space them apart, and configure them in all kinds of manners for overhung loading, high speeds, offset loads, etc. So you should really call us because we're pretty good at developing the systems in a very quick manner. So I'm going to go over accuracy levels now because a lot of the rest of the presentation pertains to accuracy levels because alignment is accuracy. So when you talk about a rail system, it's the accuracy of the combined system, the rail and the runner block. So there'll be accuracy along the length of the rail in the height direction, H, and there'll be accuracy in the width direction, which is that A3. And they're actually giving you accuracy relative to the reference edges. So in the top left part of the runner block, you'll see a reference edge. That's a ground surface, that's tolerance. And at the bottom of the rail, there's reference edges on both sides. For Bosch Rexroth, the reference edges are on both sides. In many cases, other competitors will only create you a reference edge on one side. So it's a big benefit of the Rexroth system. And then additionally, there's specs on parallelism. And you can see all the little P's and the little parallels. So just to give you a relative idea of accuracies, 90% of what Morel sells is the N class, the sloppiest accuracy, which isn't so sloppy. So in the H direction, it gives you 100 microns, 4 thousandths of an inch, and in the side to side, it gives you 40 microns. So the stock that Morel keeps, the 16 pieces, the 16 runner blocks and rails that we keep, the Sweet 16, it's all N accuracy, and that's mostly what we sell. But there are higher accuracies, and you can see as you get all the way up to UP, you can get down to 5 micron accuracy, which is very tight. So reference edges. So the way that you mount these rails and runner blocks and position them give you different accuracies. So let's look at that. So I'm showing you a picture that shows a reference edge at the bottom left on the rail and a reference edge on the top right on the runner block. And the reference edges butt up against the rail, and they need to be machine surfaces and tolerance from the engineering side on the front end of the engineering. So what a lot of people do in general automation is they don't use any reference edges. They just mount a rail and a block into the position, and it doesn't allow for any accuracy. And sometimes those accuracies aren't really needed. So when you have side loads, you really want to start paying attention to where your reference edges are. And in this diagram, you'll see that there's 2 rails and 2 runner blocks in this cross section. And where A, B, C, D is, you'll see all kinds of reference edges crowded into the rail and the block to give you exacting parallel and exacting positions. Where it's pointed to E there, you have your rail and your block, and that one is basically aligned with the master rail on the right. So you hard mount everything down and get it into position, and then you float in the rail that's on the left side, the E rail. When you have a lot of heavy loads coming from all directions, what people do is they'll add pins and mounting dowels in there, and this relieves the bolt stresses and takes the loads and keeps everything in a position. So you can see on this diagram, on the left side, there's you're trapping the rail into reference positions on left and right. And then there's no reference edge at the top, you're floating that in. On the right side, you're trapping every position. So you got the runner block trapped at the top and the rail trapped at the bottom. So that's a pretty high accuracy setup. For wall mounts, you'll see different configurations and ceiling mounts. In both these cases, you can reverse these, but you'll see that you have the reference edges on the rails on the outboard on the left for the wall mount. And then on the ceiling mount, it shows the reference edges inboard. And you can reverse these inboard, outboard. For space considerations, a lot of people will flip their runner block sideways and squeeze them in inside or outside. And it saves a lot of space. For Bosch Rexroth, for the Sweet 16 that we sell, it's the same loading ratings in every direction. So if you're up, down, sideways, rotated 90, same load ratings. A lot of our competitors will have different load ratings with directional loading. So if you're pulling up on the rail, it might have a different rating than if you're pushing down on it and side to side. And if you have really high moment loading, the best way to set this up is by having rails at 90 degrees. And if you're moving very, very heavy loads under long spans, it is okay to use multiple rails to distribute your loads across that. So if you're worried about your structure deflecting in the middle there, you can support it with rails underneath that. And you can see with this setup, you're referencing the rails parallel with a middle reference edge on both of the two sets of rails. And then there's one master runner block that sets up your position that you're fixing everything else to. When you go with a system like this, where you got 4 outboard rails and runner blocks, you are really increasing rigidity of the system. Another way to increase rigidity to your system is to increase the preload or to use rollers, a roller rail, or both. And more common than you think, a lot of people will hard mount the runner blocks down and telescope the rail back and forth, which we can help you do too. So now I'm going to turn the presentation over to my fine colleague, Ty Huser.
Thank you, Shawn. Now we're going to talk about the best practices for mounting a rail. So before we get started on best practices, we're going to talk about what is not recommended or not permitted. So if you see a rail and you open it up and it looks like that, like a spaghetti, you need to return it. But that's an exaggerated picture. This is an alignment without any aids, without referencing that edge, without a gauge or anything. You basically don't know what your accuracy is, or you don't need the accuracy, and this is not recommended if you're looking for accuracy. So on to the next slide.
And by the way, Ty, this is what happens when you pick a terrible shipping company.
Or a terrible competitor. Anyway, we don't want to dig too far there. So this is an example. Some people do this, a manual alignment. It's not recommended if you want a high level of accuracy. People can do this with the longer pieces. It will bend. It is steel, but it will bend at certain lengths. But this will achieve a lower accuracy. So we do not recommend doing it this way either. So on the next slide is one of the ways that we recommend. We do, what the red line there is a reference edge. You assemble the block to the rail, and you take measurements all throughout close to those mounting bolts to the rail. So as you go along, you can measure it, get it to the desired length or distance away from that reference edge you want, and tighten down the bolts. So this will give you moderate accuracy. On the next slide is a highly recommended way to doing it. And this does utilize one of the reference edges of the rail. As Shawn noted, there are 2 reference edges on Bosch Rexroth rail. But in this case, we're utilizing one of them. And this is a highly recommended way to doing it. This is typically a machine pocket or edge into the tooling and mount the rail right up to it, and then you get a very high level of accuracy. On the next slide, even higher level of accuracy is 2 reference edges, one on the lower on the rail, and then another on the block, which the block has 1 reference edge. And then on the other side, we do some lateral retention to squeeze the rail into the reference edge and to squeeze the block into its reference edge on typically a tool plate there that's moving the tooling around. Dive into tolerancing alignment and what are the best practices. As you can see on the screen, this is a typical application with a 2-rail system. So we're gonna, this allows us to calculate the vertical offsets. You can see that the A dimension in there is the distance between the 2 rails. If you go to the next slide, we'll blow up a chart that helps us with this calculation. The S1 is the vertical offset. A is the distance between the rails, and Y is your calculation factor. And the chart indicates the different calculation factors for the preload classes of a block. So once you get this, this is your tolerances of your vertical offsets. Likewise, on the longitudinal, the two blocks on a single rail, it also has a vertical offset that can be calculated. Again, it is a function of the distance between the two blocks. And if we go to the next slide, we'll blow up the chart, and similar calculation, the S2 vertical offset will be equal to the distance between the two blocks, B, and the calculation factor. And that is dependent on the block, if it's a standard length, a long length, or short. Now there's also a parallelism tolerance that we can calculate. And this is when you're using two reference edges on two rails. So this is a chart based on, dependent on preload, but it's also independent on the rail size. It doesn't matter what the size of the rail is. This is the same kind of tolerancing that you can expect. So there's different levels of precision there. There's the standard installations there in the middle, and this is what you can expect for your tolerances on parallelism. Roller rail is a little different. The parallelism is dependent on the size. So same type of chart, just look up the size, look up the preload of the block, and this is on two rails that are referenced.
Hey, Ty,
Yeah.
if I might add something, the reason why people only use one reference edge is because then you can float in the other rail and you don't have to worry about parallelism, because your rail will self-align to the master that's already referenced against their edge. So in a lot of cases, you'll see people that are only referencing edge on one of the rails and then they float in the other one, and that's very common machine practice.
Yep. That's what I see most too. So, okay, we'll go to the next slide. This is a block that has a hole in it, and we actually order it this way, but this is an aid that Rexroth sells that helps float in that second rail that Shawn was talking about. So if you go to the next slide, you've got a picture of the top rail there that is screwed down and it's referenced, and that's your master rail. And you want to float in that next one. A good way, or this is an easy way to do it, is that you take that block with the hole in it and you position it over one of the mounting holes in the rail, and then you measure, you move the rail where you want it to be, and then you screw down that mounting bolt, and you just move it along the rail using that gauge as a measure of how parallel you want it. So this is a good way, an easy way to float in a two rail system. Okay.
Great. Thank you, Shawn and Ty. And now it looks like we have a few questions. Our first question is, how many references does your rail have and how many does the block have?
I'll take that one. The rail, all rails come with two reference edges. This is standard for Boss Rexroth for many years. There's other competitors out there that only have the one reference edge, but we do have two on all rails. The block has one reference edge. It's easy to look and to see which reference edge is the reference edge, is the one without the part number. The one with the part number, it's not the reference edge, so it's easy to determine.
Great, thank you. Excuse me. Our second question is, how can you use different accuracy blocks and rails, and does that change the overall accuracy?
So the answer to that question is you can mix and match for Rexroth systems, the different accuracy classes. So you can have an N accuracy block and a UP accuracy rail, and there are different combinations that create new precisions and accuracies. So we could help everybody through that. It helps leverage our inventory. So if something's not available, we can still offer you other precisions that you can get. A lot of other companies won't allow that.
Great. Well, I'm looking in our chat and it doesn't seem like we have any other questions. So I'll wrap up and just thank Shawn and Ty for answering our questions, and to thank all of our guests for joining us online this morning to discuss linear bearing alignment. I would say if you have a question and we weren't able to get to it, maybe I didn't catch it in the chat, please email us. You have Shawn and Ty's contact information here, and we can get back to you after the webinar. And you can also contact them for support with your linear bearing systems. And again, join us for part 3 next month, where Shawn and Ty will discuss how to avoid bearing failure due to things you can predict. Thank you for attending Handling Offsets and Misalignments by Morel Group. Have a great day.
Thank you.
Thank you.